and hopefully you can all see my screen okay. Welcome everyone to our second session of the virtual conference on epistemic uncertainty in engineering, where we focus on the key main topic of today, which is computing with uncertainty, with Ziet and Krenovich. And our schedule for the next few days, just to make sure everyone's up to date. Our next talk will be Manifesto on Uncertainty on the 15th of February at 10 o'clock GMT, where we'll be featuring Thierry Deneau and Michael Goldstein, where they discuss at the end, can we agree on anything about handling epistemic uncertainty in engineering? After that, we have some more talks on the 17th of February, the 3rd of March, continuing on throughout the following month. Our agenda for today will be BFF, not best friends forever, but Bayesian, Fiducial, and Frequentist uncertainty quantification by artificial samples, followed by a Q&A with Professor Minga Z, epistemic versus aleatory granular computing and ideas beyond that, plus a Q&A with Professor Vladik Klenovich, and that'll be happening at 5 o'clock. And then finally, we'll have a 30-minute conversation about what would be unified uncertainty calculator would look like. And that'll be lasting for 30 minutes. Yesterday's session ran slightly over. We ended the formal discussion after 30 minutes, but people are more than welcome to linger around for continued debate and conversation. So I'll pass the stage to Scott to introduce our first speaker.
Thanks, Francis. Welcome everyone to our second session. I'm very pleased and proud to introduce Minga Xie. He's a distinguished professor in the Department of Statistics at Rutgers, the State University of New Jersey. He's been working on the foundations of statistics and fusion learning, and he's obviously a very big name in confidence distributions. His BS degree is from the University of Science and Technology, and his PhD is from the University of Illinois at Urbana-Champaign. He's a fellow of the ASA, and we're very excited to have him here today. Minga?
Okay, let me share my screen. Can you see my screen?
That's perfect.
Okay. Thank you, Scott and Francis, and thank you everyone for tuning in. I'm really glad to be here. What I'm going to talk about is a union of Bayesian fiducial frequentist approaches, especially uncertain quantification by artificial samples. The task, how can I move? Okay. The task of statistics is to infer the underlying truths based on observed data, and the inference typically includes uncertain quantifications. So that's why I believe that's the sequence over here. I'm giving a talk here. Can you hear me?
And I just trying to make sure.
I can hear you fine. Sorry, I'm just going to mute the other person on the call.
I think one thing I need to have animation over there. Is there any way I can put in animation going over to talk about not just
Sorry, I'm just trying to find out who that is. Can you please make sure that the microphone's muted?
I think it's Juan, actually.
Wrong, but I want to have see.
Sorry, let's see, something is going on. Let's see, what is this?
Francis, maybe you can mute everyone and then unmute Minga.
Let me just share one more time. Just want to see whether.
Let me see. Let me move things around here quickly.
Just want to see whether I.
Okay. Is this okay now?
I think that's okay. Is everyone muted? I think so. Hold on, I'm just going to make you co-host, Scott, because that was a little bit finicky.
Okay, let me share my screen again. Sorry.
Apologies about that. Yeah, apologies.
Okay, we're
Please
back.
continue.
Okay, most of researchers are probably more familiar with the competing narratives of Bayesian versus Frequentist. The third, less known Fiducial inference, was actually pioneered by I. Fisher in attempt to define an inversion procedure for inference as an alternative to the Bayesian method. Each of these paradigm has its own strengths and limitations, subject to different kind of philosophical kind of thinking. This talk actually intends to bridge these three different inferential methodologies through the lenses of confidence distribution and simulation. And we hope it's going to be, by the end, is indeed a best friend forever. Here is the outline of my today's talk. At the beginning, I'm going to briefly articulate the logic behind the CD development. Although confidence distribution is a purely frequentist concept, but it links to both Bayesian and fiducial inferences. Based on development, I'm going to make a case for the union of the Bayesian frequentist and fiducial inferences. And particularly, I'm going to emphasize on 2 points. One is going to be artificial sample data for inference. The other one I want to highlight is that we're going to promoting that under each paradigm, a single parameter has both 2 versions, fixed and random. And finally, based on our discussion, I have 1 slide to make perhaps kind of very naive reflection on epistemic versus aleatory uncertainty, which is trying to fit the thing of this similar sequence. Okay, let me go back to the full screen. Probably better. So what is confidence distribution?
Sorry, Minga, I think the screen's gone black again. Would you mind trying again?
Yeah, okay, I need to try again. Sorry.
No problem.
Yeah, that's full screen, right?
Yeah, that's perfect.
Okay.
Please continue.
Thank you. In statistical inference, actually, we typically use a single to estimate parameter of interest. The idea of confidence distribution actually it's straightforward. It just use instead a sample-dependent distribution function on the parameter space to estimate parameter of interest. For example, in this toy example, we can estimate by a single point or an interval for the unknown location parameter, but we can also use a whole curve, a function, to estimate parameter of the interest, the location parameter. The idea of getting similar to the Bayesian posterior distribution, confidence distribution is also very informative because it's a function to estimate parameter, right? So you can derive from the function the point estimator, confidence interval, and p-values. This is an illustration of that. And then this is a particular example. From this toy example, you have this distribution estimator. The center, location, or median will be a point estimator. And confidence interval is just look at the tails, and then you can get confidence interval. And for hypothesis testing, you look at the tail probability, give you the p-value for hypothesis testing. The definition of confidence distribution in a single English sentence is that a confidence distribution is a sample-dependent distribution function on the parameter space that can representing confidence regions of all level for a parameter of interest. You can just we can just simply use that 1 English sentence to describe it. Diacox actually has a very good summary about what the CD is. He mentioned that the confidence distribution is to provide a simple and iterable summary of what can reasonably learned from the data. Of course, on assuming the model. Based on definition, the confidence distribution, actually the concept is very broad. I list a bunch of over here. For instance, the bootstrap distribution, right? bootstrap distribution is a sample-dependent distribution function on the parameter space. And it can representing based on a bootstrap distribution, we can derive confidence intervals and confidence regions of all level for the parameter on the target. The next slides, actually, I'm going to argue that likelihood inference is a special case of under the framework of confidence distribution, inference using confidence distribution. Well, everyone knows that likelihood function is a function on the parameter space. It contains tons of information, all the inferential information about parameter of interest. Likelihood function is not density function on the parameter space. It is only the kind of multiplier of density function of data given theta. It's on the parameter space. It is not density function. It's just a curve. But however, the likelihood function, we can normalize it so that underneath the area is 1. So in that sense, for example, in this toy example, we can easily write out the likelihood function. And if we normalize it, it's become a density function. And this density function is exactly the confidence distribution we're using in this toy example to estimate parameter of interest of the location parameter. Confidence distribution also linked to hypothesis testing. For example, in this toy example. And when we do the hypothesis testing, we can kind of easily calculate the p-value according to standard procedure. Just go write out the p-value. And the p-value function, when we let the non-hypothesis mu0 varies on the parameter space, this has become a curve. This has become a curve because it's a function on parameter space. So you plot it, it's become a curve. This is a cumulative distribution function of this particular, confidence distribution we talked about in that toy example as well. Okay, so you can see that actually confidence distribution can derive from likelihood function, can also derive from hypothesis testing. So this is actually the bunch of ways, common ways that we have been using to derive confidence distributions. Confidence distribution has 3 forms in presentations. In this toy example, we can use its density form, plot the density function, and then this is very similar to the Bayesian posterior. Bayesian posterior typically was plotted in a density form. And of course, in the kind of p-value function case, hypothesis testing case, then we have this cumulative distribution function. And then this is kind of CDF version. This is confidence distribution as well. And then the other one is called confidence curve. Mathematically deriving it, you can see that mathematically is derived actually from the confidence distribution. The nice thing about confidence curve is that you can vision this has very intuitive explanation of what confidence curve is. You can see that it's essentially stacking up confidence intervals of different level. Stacking up become a curve. So you stack up the 99, 90, 98, 95, 90, 80, and etc. You stack them up, the endpoints form a curve. And this curve is called confidence curve. And this confidence curve actually gives you confidence intervals for all levels. Okay. Another thing I want to make case is that confidence distribution is also related to C-box. Many in this audience are very familiar with C-box, and we have expert here as well. And then in the case that when there is something unknown, like under the Dempsey-Schaeffer calculus, in this case, actually, we promoting, in other frameworks, we're promoting so-called lower and upper CD to look at the upper distribution of lower distribution bound. So this is essentially when I plot the upper and lower CD off in this graph, you can get the familiar C-box plot, right? You get the lower bound over here and upper bound from the up CD, right? So this lower and up CD, then you get in this lower bound, upper bound. And then from this, the relationship between, we have the relationship between confidence distribution and confidence curve. We can plot these two confidence curves of this upper and lower CD. And this one actually form a joint confidence curve with the lower upper CD, give you confidence intervals of all levels, and then from all the levels pi up. Okay, so this is the same thing of that. So you can see that confidence distribution actually indeed is not strange. Concept has a lot of connections with existing inference tools. Here, for the interest of time, I'm going to skip this couple example. What I'm going to say is that the confidence distribution actually is very broad. We have seen that from the bootstrap distribution p-value function, normalized likelihood. If we normalize the empirical likelihood, we also have the same thing. Then later, I'm going to argue the Bayesian posterior often also is a confidence distribution. Of course, the fiducial distribution, etc. So one thing I want to emphasize is that as long as we can, the approach can be used to create confidence intervals or level, regardless is a parametric model in a parametric way or non-parametric way, whether it has a normal assumption. The toy example with a normal assumption, but in general, we do not need to have that. And even we can have asymptotics. And as long as we're way to increase that, we can get the confidence distribution, derived confidence distribution, and covered by confidence distribution framework. So our understanding is that typically, this very brief introduction of confidence distribution is that any approach, regardless be how you derive it, as long as can be used, can be unified under the concept of confidence distribution, as long as it can be used to build the confidence regions or confidence intervals of all level, exactly or asymptotic. Okay. This confidence distribution providing us a very like a new methodology framework to develop new methodologies. And then today, actually, we're not going to emphasize on this new methodology development. We're going to emphasize to make the case of the union for the BFF. So let's move on to the second part, try to make the case for BFF union. So with the concept, the first concept is that immediately is kind of conceptual union. Immediately from the confidence distribution, we know that it is a function estimator of the parameter or distribution estimator, distribution function estimator of the parameter. And then this immediate question is how do these compare with posterior distribution and fiducial distribution? Both are the distribution estimators of the parameter. You can view that. And this relationship actually, I'm going to talk about the slides, is very similar to this consistent estimator versus MLE in the point estimation framework. It's not exact, but it has some similarities. I'm going to make the case of that. And the second union actually is I'm going to spend a lot more time, is basically trying to make a case for the artificial sample for uncertainty. Is the randomness is actually for uncertainty. And create the equivalence of all these four different distributions. At the first level, actually, when we talk about confidence distribution, Bayesian posterior, and then likelihood function, bootstrap, etc., all this kind of list over here, they are all distribution estimator on the parameter, and they have two bullets. The first bullets, they are dependent, sample-dependent functions. Any of this Bayesian posterior and likelihood function are all based on observed data, right? It's sample-dependent distribution function, and they are on the parameter space, functions on the parameter space. And all these methods can use to make statistical inference to create confidence intervals, confidence regions. So that's based on these two criteria, this is exactly fitting to the definition of confidence distribution, okay? Of course, people will say they actually isn't not quite the same, right? So what's the difference? This is all the question have asked us quite a bit. So let us first dissect the one English sentence of the definition of one English sentence of confidence distribution. What that means is a sample-dependent distribution function that can represent confidence intervals of all levels for a parameter of interest. Actually, that has two things. Requirement is essentially for a definition of confidence distribution. The first is when you given observed data, it is a distribution function on the parameter space, right? It's a curve, it's a function on the parameter space. The second one is that it's quantify the performance, is that this function, based on this function, we can derive confidence regions of all levels, so that essentially this function is informative. We can derive from, based on this function, confidence regions of all levels. So that's basically what it has. You can kind of compare with this confidence distribution in the toy example. It is a function on the parameter space, and based on that, there's a performance of this function, which is we can derive confidence regions of all levels. Okay, so this is a definition. Remind us in the point estimation framework that definition of consistent estimator, or the definition of unbiased estimator, right? The point estimator, so consistent estimator, unbiased estimator need the point as a sample dependent point on the parameter space. And second thing is that the performance, of course, consistent estimator, the requirement of performance is different from unbiased estimator, but regardless, they are quantifying the performance of the consistent estimator or the performance of the unbiased estimator. So that's how we define consistent estimator and unbiased estimator, exactly using these two requirements. So with this in mind, so you can put the consistent estimator one side and MLE on the MLE estimation and other point estimator on the other side. Okay. So the breakdown of the confidence distribution in that definition, we see that we did not use any tell you how to get the confidence distribution. It just tell you the performance, describe the behavior of the estimator. And then for like in the MLE and estimate case, all this method, including bootstrap, Bayesian method, likelihood approach, p-value function, there's a procedures, there's a steps, there's a inductive reasoning leading to that how you create the distribution estimator. So this is very much similar to the case versus the MLE versus consistent estimator. And then I had kind of often a joke with my friends in Fiducial, doing Fiducial Inference or the Bayesians. I say, hey, you are my MLE, I'm your consistent estimator. In the sense is that most time MLE is a consistent estimator, but of course it's not always, you can have a stranger case. But the consistent estimator is the broad concept. It's not only including MLE and also other kind of moment estimate as long as it's consistent from other methods you're deriving the estimator as long as it is consistent. So this is conceptual wise. You can see that the definition of confidence distribution and the fiducial distribution and bootstrap distribution, the relationship is that distribution estimator, that's kind of you put them in perspective. They all distribution estimate sample dependent distribution function on the parameter space. And then one method is quantify the performance. The other one is tell you how to derive it. It's setting up the equations, solving equations, maximization, minimization, etc. It's all using Bayesian formula. Okay, so that's, I hope that is okay. So this is basically the first unit on conceptualize kind of under the framework. Then actually I want to make a case a little bit more. Is this second much I thought is a deeper rooted union is the artificial randomness for uncertainty. So particularly I'm going to emphasize that later on make a case. There are two versions of parameter across each paradigms. So let's start with the bootstrap. The bootstrap is very familiar in the statistics community and also other fields. So the bootstrap we know is a resampling approach, and then we simulate the fake data, right? Then based on the fake data, we would be able to get the estimate, bootstrap estimates. Why bootstrap estimates works? It's because of this bootstrap central limit theorem. In this toy example is this form. So what does the bootstrap central limit tell you is that the randomness, I'm sorry, let me see. The randomness on the left side is actually conditional observed data. The randomness is only the artificial, like fake data randomness. You are resampling randomness, the Monte Carlo artificial randomness. And then why the bootstrap works, because this artificial randomness matches with the sample randomness under the model. So that's why the bootstrap works. That's kind of the first time this was derived of that. Actually, our CD development, this is my late colleague, we worked together to start it with confidence distribution, the project confidence distribution. And then actually in the beginning, one of the task was trying to understand what bootstrap distribution is in the statistical framework, and eventually that's to the development of confidence distribution. So in some sense, CD can be viewed as extension of bootstrap distribution. I hope this is clear. So one side is artificial randomness. The other side is sampling randomly. This is a match, so the bootstrap works. So how about the confidence distribution? And the confidence distribution is, we know that it is a distribution estimator on the parameter space. And as a statistician or probabilist, we know how to simulate generating from the distribution, right? Simulate, or CS people can know how to simulate from the given distribution. So for example, in this distribution estimator, we can generate a random number from given data. We can generate a random number from distribution. We call this a CD random variable. We call this so-called CD random variable. And the CD random variable actually can viewed as a random estimator of the theta. In this toy example, you just generate that. This is actually a random estimator of the underlying mu location parameter. And if we rewrite it, this equation, if we rewrite this equation, exactly we can rewrite that in the form of the artificial randomness given data. It matches with the sample randomness again. So this is exactly the same as the T justification for the bootstrap distribution, why bootstrap works. So we can see that essentially we make the case that CD random variable play the same role as a bootstrap estimator. This is actually why confidence distribution works, is also because of the simulated randomness in CD random variable would match the sample uncertainty in the estimation. So you do see that the artificial randomness actually, when it can be match the sampling randomness, then we will be able to make inference based on these artificial samples. A part of the reason that on the right-hand side, the sample randomness, we won't be able to do much because we only have observed one copy of data. The sample randomness is actually theoretically derived from your assumed model. You cannot repeat it in the frequentist. You only have one set of data. You cannot repeat it doing it again and again. But for the artificial randomness, you fake data, you can generate as many as you want, right? So that the randomness from artificial data actually matches with that. It allows us to have a way to do statistical inference. Now let's move on to the fiducial connection. I think many of you have here probably heard of fiducial, but I still want to use a couple of slides to introduce the fiducial idea, just in case. So just look at the toy example for simplicity. That's n equal to 1. I have only one observation. So this is a normal sample. Y equal to this distribution from the normal can be rewrite as this kind of data generating equation. Y equal to mu theta plus u. So this is basically that. The fiducial idea is actually do the inversion. So that's inverting that our target is the theta. That's inverting the theta equal to y minus u. So in this case, then we would have this equation. This is y equivalent to this one. Then now we observe the y, right? Y is observed. So we plus the y observed. This is observed and then plug it in. And then u is from the normal 0, 1 distribution. So the theta essentially, after we observe the u, then with theta has a normal y1 observation. This is a so-called fiducial distribution. But of course, we know that there's a flaw in this argument. But regardless, this fiducial distribution actually matches with like posterior with some posterior distribution with certain prior, and also matches with common distribution what we're using. It's actually very informative to estimate the parameter of interest. Very effective distribution estimator to estimate parameter of interest and location parameter estimated theta in this case. What's wrong here is that actually when we observe the u, you look at the equation, the randomness of these two things, left side is y, right side is u. The randomness are completely dependent. When we observe the y, we also observe the u as well. So instead of the bigger y, the big u here should be smaller u. So this is exactly talking about that. When you observe y, the u is degenerated as single u, even though we don't not know. So we can rewrite this equation as this equation. So in this case, I kind of jumping back with the n case. So y bar equal to that. Actually, we can observe is the y bar, and where is observed realized, and corresponding to it is not capital U. Is not capital U. is the error, is the realization associated with this observed y bar, okay? Although it's unknown, but u is unknown. So we re-examine this equation. We say, let's make an inference for, we still want to make an inference for theta. Y is observed, u is realized from this known distribution, but I don't know which u it is. So how do you solve this problem essentially? So y bar is completely known, u is halfly known, right? It's just known from, is a realization from that. We don't know which value. So one of this kind of artificial generating sample is that let's do a random estimator for the u, generating from the distribution and treated it as if it is u. So that's the idea of intuitive appealing assumption, is that basically let's do the artificial sampling when we do generating this, right? And the u is to estimate that. And then we're plugging back into that, we get the random estimator of theta star. And this theta star actually form a fiducial distribution. And this theta star is also from a CD distribution, is also that, so is also the CD random variable. Theta star is a CD fiducial sample and CD random variable. So this is actually, you see that this is actually connection of the fiducial. This is kind of, in this way, is kind of another interpretation of what the actually fiducial inference inversion is doing, is use the random, is using random artificial u star to estimate the unknown realization, and plugging back into the equation, get the random estimator of theta star. That's essentially fiducial inference is trying to do, to at least to our understanding. And then in general, they can do the same thing. You have general, this is a model instead of the special case we talk about. And then we have a realization. When we have realization, the u is realized unknown, and then y is observed, of course. And then we want to solve for theta. But we do not know what theta. We simulate the u star from the known distribution and plug that in, solving for theta star. Then that's basically fiducial inversion in the general form. That's how we do that. Yeah, but of course, sometimes this cannot be exactly solved. There's no solution for that. Actually, this is Jan Hannick and his colleagues have developed so-called generalized fiducial inversion algorithm, just particularly targeting the general case beyond the pivotal statistics or not well-defined inversion problems in the case that there's no solution in this in the fiducial equation. So they use optimization to do it. But they actually, the interesting question is that Yang and his colleagues have proved this so-called fiducial Bernstein-Volkmann theorem. And I'm rewriting their theorem into this familiar form. Again, the fiducial artificial sampling random estimator from the fiducial kind of inversion would exactly, actually the randomness would be matched with the sample randomness of our target. That's why the fiducial inference first order asymptotic is right under very general conditions. So this is because of fiducial Bernstein-Volkmann theorem. Okay, so I hope I have made a case that fiducial sample is the same as a CD random variable, essentially equivalent kind of concept, and also equivalent with the bootstrap estimator. They are random estimators of the parameter. Again, we emphasize the match of simulated randomness versus sample uncertainty randomness. So the question is that BFF leaving out that B. What does the B look like? The B actually, let me ask the question, is that the same framework as the fiducial setup. We do have a general data generating algorithm, data generating model. And then we have a realization, Y is observed, U is a realization but unknown. It's a realization from a given distribution but unknown, okay? So the question is that we try to make an inference about theta, and then Y is observed, and then unknown U is realized, the same as the fiducial equation. But of course, we know that Bayesian has additional prior assumption. The prior assumption tells us that the theta, what your target, the theta is a realization, the data coming from this data. And this data is a realization from a given prior. So the theta is coming from a prior. So that's basically, this is a blue one, is additional knowledge you have for the Bayesian inference. So given this one, how the Bayesian solving this problem? That's the question, right? In fact, actually, Bayesian has a really nice solution for that, specifically that particular solution. That solution is a Bayesian inversion, which is called Approximate Bayesian computing method. This is a likelihood-free kind of a Bayesian, just doing the Bayesian inference without likelihood, without explicitly knowing the likelihood, or using the Bayes formula. So the idea is very...
You have 5 minutes left.
Oh, okay. Oh, so I should speed up. So you can see that what is the approximate Bayesian? So it's the same thing. You have a theta is realization from the pi, u is realization from the d. You are generating from them, and then you get your fake data. If the fake data matches with your observed data, you keep the theta. Otherwise, you just throw it away and going back. This is a rejection sampling method. So effectively, the capta theta star is you make the solution of this equation. You generate the u star, you solve this equation among those generated theta stars. So this is actually incorporate both information of prior and the uncertainty in the distribution in the model. So there's a theory. I'm not going to have time for that. And then this actually theta star form a so-called ABC posterior. And this ABC posterior is approximation, actually is a very good approximation to the Bayesian posterior. Of course, the real ABC is a little bit different. They have allowed matching errors, and also they use sufficient statistics, summary statistics. If the summary statistics is sufficient and the epsilon, the matching error goes to 0, this is actually the ABC posterior is exactly the posterior. Of course, if it's not sufficient, there's a little bit more complicated. I'm going to skip that slides, like Cauchy example. The thing I want to bring to the topic is that the Bayesian inference, right? You have a posterior distribution. Then you typically we use MCMC or all the method to do it. It's basically we're generating random theta star, random theta from the posterior distribution. So based on the version of Bayesian Bernstein-Waldman's theorem, we also have this kind of very exactly matching we have looking for, is that the artificial randomness, right, from you simulate MCMC, whatever you get from the posterior distribution, given data, is going to be matched with the sample distribution from your model under the Bayesian Bernstein-Waldman's theorem, when sample size goes to infinity. So you do see this familiar matching again. So essentially, you know that the number you generated from posterior distribution actually is the same as a fiducial sample, as a function-wise, it's the same as a bootstrap estimator, and it's also same as a CD random variable. So these similar randomness, again, the emphasis for the inference is a simulated randomness matches with sample randomness. Of course, sometimes this is Bernstein-Waldman's theorem is first order, actually higher order result also exists in all settings as well. So this brings us to this very kind of the table is that in fact, actually, we're promoting two versions of the parameters. One is the random version. You can see that in Frequentist, typically talking about that true parameter value is a fixed version, but there's a random version in the Frequentist case. This is CD random variable is a random parameter for the Frequentist case. Bootstrap estimator is also random parameter for the case. And the Fiducial, I just skip that. For the Bayesian, actually, Bayesian indeed have two versions. Emphasis has been placed on the random parameter in the Bayesian inference. But then actually theta is also, Bayesian in the case is also the theta 0. So I hope I still maybe a couple more minutes for me. So this is basically, the randomness is for uncertainty. And then there's a fixed version is actually the true or realized value. So for the Bayesian, actually, let me go back. This for the Bayesian to make the argument of Bayesian have both fixed and random case. The target is fixed, and then the randomness is for uncertainty. So this one, actually, we can go back to the Bayesian, the billet table experiment, okay? It's trying to play, there's a God version, the truth, and then the human version is what we observe. From what we observe from data, what we're trying to understand the truth. So this is the truth, the billet table truth, is that we have randomly thrown a black ball onto the billet table, and the measure the landing place horizon line is basically theta is 0.398, something like that. And then the randomly throw additional balls onto the billiard ball and recording how many on the left of this line and how many on the right. And then the question is that given this number of how many on the left, well, how can you infer the theta zero, the true theta zero? So that's basically where the black ball was landed, the truth, right? The black ball landed. So this is actually a human version. I only give you that 6 ball out of the 13 is landed on the left side of the black ball. And I will try to infer what the theta zero is. You're not infer a random theta on this 0, 1 interval, is try to understand where the black ball was. That's 0.39. So that's what I want to emphasize on that. So in the modern day interpretation of the billiard ball model, you have a model is landed of that, and then you get posterior, etc. But I want to emphasize that we really interested in inferring is what theta zero is that black ball landed place, is that has a true value, which is 0.398. Is not a random theta, what you are making inference. So that's why I want to emphasize that. Even though we thought that in Bayesian inference, theta is random, but actually the target for the Bayesian inference is the theta zero, where the realization of the prior was. Okay. So anyways,
if you're able to wrap up, that would be really appreciated. Thanks.
Yeah, I'm going to wrap up. So I'm going to just wrap up of this. So this is one slide or reflection of the of this two uncertainties. So Bayesian actually method is indeed is an odd one out compared to Fiducial and the CD inference, the Frequentist inference. It's because it has an additional assumption on the prior distribution. I think everything is the same except that the Bayesian method has a prior assumption. And because of prior assumption, there's no data, right? There's no data involved in the prior. So that's why we adopt the system and the philosophical argument of the epistemic probability for the Bayesian inference. The likely part has a sampling interpretation, but then for the prior part, they don't. However, sometimes we can think of the priors, the historical is the priors coming from the data. That question is that, for example, in Bayesian, for the Bayes, in his Thomas Bayes, in his experiment, how did he know that the prior is uniform 0, 1 when he threw a ball? It's actually there was assumption, and also he tried it many times. It's not too far from that, right? There's a historical data from there. So in that sense, if we can thinking of the priors can be viewed as a sampling uncertainty of historical data, then perhaps the posterior uncertainty can be viewed as also the sampling uncertainty from historical multiple the current data, if we are willing to do that. Furthermore, we can push a little bit further. Actually, we not necessary to use the historical data. We may be thinking about the sampling, Monte Carlo randomness actually can be replaced at thinking this experiment we do the Monte Carlo, we say we're mimicking, this Monte Carlo was mimicking the historical experiment. And then this one will give you this sampling randomness. It's not artificial, aleatory uncertainty of sampling randomness, not just the real data and also artificial data. Okay, so this is my last slide. Well, I think this is a summary. I provide a brief introduction of confidence distribution and the idea of distribution estimation, and try to make the case of union of BFF concepts. And then for a valid inference, we highlight the need of matching this the sampling uncertainty with the randomness of artificial sample data generating scheme. Okay, thank you very much. I hope I'm not too much over time.
No, not at all. Just trying to manage the time and let you know. Thank you for your talk. That was really excellent. Does anyone have any questions for Professor Minge?
It's Vladik. I have a question. Thank you very much for the very interesting presentation. It's indeed kind of enlightening and everything. Question is, sometimes the prior distribution, and I'm kind of finding myself in an unusual position of kind of defending a little bit of Bayesian approach. Sometimes prior distribution comes from an expert and describes kind of intuitive expert opinions. Can you describe that in these terms of this BFF approach? Since you are mentioning that this approach kind of generalizes all existing approaches.
Yes, actually, we did have a paper published, I think 2014, is about incorporate expert opinion into clinical trials. So in that one, we did make the argument the expert actually, the prior is a CD based on the historical knowledge. In the sense, you can imagine that where the expert get their intuition there is probably is summarized from their data, from the involvement, the physicians, the expert in our case is the physicians to see the patients. After they see the patients, give the prescribe the drugs to the patients, they observe. So this is based on their historical the patients, and also from not only their historical patients, and also their colleagues' patients, historical patients, because they talk to the colleagues. Colleagues say, hey, this is a drug is effective for this treatment, etc., because they all based on their experience. It's not like they just deriving from anywhere. So that what we kind of making argument, if that's the historical, thinking this historical knowledge has some sort of sampling data coming from, then you probably can treat that as a CD, and then we combine that. So that's actually the argument. And then that place actually Bayesian had the issue in that particular paper because it's binary, bivariate. There's kind of very strange phenomena, and then that was published in Annals of Applied Statistics.
Thank you very much.
Yeah, thank
Are there any other?
Yeah.
Go on.
So you mentioned that a confidence distribution is similar to a C box. So my question is this: when should I choose a confidence distribution over a C box? Does a confidence distribution quantifies inferential uncertainty better than a C box?
Okay, thank you for the question. Actually, that's one thing I want to point it out. I didn't get a chance. The C box is actually typically good for the case when you have an unknown uncertainty, right? If there's no unknown, like in this case, everyone yes or no, if there's no unknown there, these two curves match with each other. And this upper and lower bound match with each other, or asymptotically, these match each other if you have large sample, even in this case, in this binary Bernoulli case, you match with each other, right? When you match with each other, actually, this is confidence distribution. So confidence distribution, the C box is there. There's not necessary. There's no competing of these two. The confidence distribution I was promoting here is that there's no situation there's no unknown situation. Yes, no, and unknown. I don't have this unknown like Dempsey-Schaeffer, this unknown situation because it's a curve. It's a single curve, or it's or asymptotically single curve. But you do need to quantify the uncertainty with the more finer uncertainty on the small sample with unknowns. I would say C box, and then it's equivalently C box. What we are doing is exactly equivalent to what we're doing the upper and lower CD. And then recently we have tried to make this argument in some of these articles, in recent articles. So this indeed is the case. Same thing. This will be matched with the Ryan Martin and Changhai Liu. Their IM framework is the same. So they have what is a belief function? There's a possible function. This is a law up CD is actually matched with that as well. So this is just if you want to quantify the uncertainty with fine uncertainty with finite sample with unknowns, the C box or law up and CDs will be right way to do. If you care about only asymptotics and then don't have this unknown situation, then these two curves are the same. Then this goes back to the confidence distribution I'm talking about most of the time. Yeah.
All right. Thank you.
I was wondering, does the introduction of like Bayesian information into this not make it difficult to keep the guarantees of coverage that are necessary for the confidence distributions to be valid confidence distributions? Yes,
that's exactly right. We are aware of that, right? So Bayesian and the Frequentist inference only match. There's only situations either in the situation that the prior is very special kind of prior, so they're going to be matched, or objective-based type of framework, or that sample size n goes infinity, so that the prior information washed out, don't have much impact. So every information more or less coming from likelihood, and then you have this Bernstein-Montes theorem. So that's the situation, the Bayesian and CD matches. But in the small sample, I totally agree with you. If you are not willing thinking that the priors are coming from historical data, and then you were thinking you're not willing to make an assumption, then the Bayesian posterior would be different from the frequentist CD kind of inference. So that's definitely, I can see that. This is similar to the MLE and then the consistent estimator, right? I have this kind of put in here. In most time, MLE is a consistent estimator, is the largest sample, etc. But you do find the cases in the MLE situation, it's not consistent estimator. It's the same thing that I claim that they have connections, but there are cases in the Bayesian inference, especially small sample, specific kind of certain type of class of priors, then the confidence distribution and posterior distribution won't be able to match. This is similar in the special case. Occasionally, the MLE does not match with the consistent, is not consistent estimator. So this is the same kind of phenomenon to me.
Yeah, it's just about being aware of when that is happening.
Right.
Just making that trade-off to be able to incorporate additional information from the Bayesian posterior.
Right. Right. This is need to be aware of that. One thing is that they were going to match is that under those kind of objective-based kind of framework, then they will match, right? This is kind of Jim Berger and their group have been directing that. And the other big class is the just asymptotic. So I can see that outside of that, we will need to be more careful whether they will match. That's typically I will tell my students or my or others, I would say, to watch out if you have small sample Bayesian, and then the prior is not objective prior, then data is not large, and then that probably the frequency, the frequency statement based only on the observed data, whether that still holds, I'm not sure.
Okay, thank you.
Thanks.
Can I ask Francis?
We have 5 more minutes for questions.
Thanks. Okay, so hi, thanks for a very interesting presentation. You've shown the model at some point, the generalization to a model G. So I was wondering if you've done any work or you have any experience on, or whether you can comment on the situation where G, the function is not defined or is not known, or whether you have any comment on the non-parametric case or the model uncertainty case.
Okay, very, very nice question. This G actually is in general form, we say it's a given. And then this not necessarily, it's algorithmic model. This I would put in that way. So in statistics, we call it a structure equation model following Don Fraser, but in CS literature, this is more like an algorithmic model. So actually, we do not need to exactly know the G. For example, you have a differential equation models. You have sequence of differential equation models. It's fitting into this framework. It's only that I give you a parameter, I can generating U, and after U, I can kind of go through the bunch of simulations, can get the Y. So that's the only thing what you can have, this algorithmic model. You just imagine what you get a Y, right? This is G is algorithm. So you can have input your theta. Is a given algorithm, of course, it's given model, it's given algorithm. So you input your parameter, and then you generating your noise, uncertainty noise, and then generating the data is generated. And you assuming your observed data is one of this generated noise, realization of this one generated noise for a given true parameter. So that would do. So this is G. Do not need to explicitly know is that case is that as long, for example, the algorithm is like differential equation models, like in the astronomy framework. We can use this in the astronomy field. For example, you know the Big Bang is starting from giving you the parameter of energy and things like that, and you starting to do the simulation, starting putting the uncertainty simulation in there, and then you have expanding of your universe, and until now you observe this. So that kind of sequence of differential equations that will be still fitting into this framework. This is actually matches with very well. I was give a talk probably 3-4 months ago with a CS group of people, but G, you can even thinking of the neural network model.
So do you think that does this function need to have any regular properties or any properties at all, like in terms of continuity or monotonicity, or can it be any type of function?
Yeah, I think this is an excellent question. I do not thinking this is let me put, if you want to, like in this framework, in the Jan Hannick's work, the G, you need to have some conditions, you need continuity in certain way and things like that. And in his work deriving the Fiducial Bernstein-Bowman theorem, there are imposed conditions on theta, for example, differentiable or things like that. And then, but in general, I do not see that a case. If you're thinking of this like Bayesian, approximate Bayesian computing framework, what kind of algorithm the Bayesian ABC would be able to use? That's pretty much the framework that the G is. It can be very general. Do not have even continuity. I don't know. Even of course, there's an issue. For example, in the deep neural network, there's the issue of identifiability, model identifiability issue. You could have multiple theta generating of same Y. So how do you define that? That's another task of inference. It's not the model issue.
Right. Yeah. Yes. And not only neural nets, also in simpler model, you can have those kind of situations.
Right. Right. So you have to define what your target of inference. Yes.
Sure. Okay. Thanks very much.
You're welcome.
All right. Thank you very much. Let's thank our speaker again, and we will move on to the next speaker. Thank you very much, Professor Minge.
Thank you, Francis. Thank everyone.
I'm just going to stop sharing your screen, and I'll pass over the floor again to Scott to introduce Professor Vladek Klenovich. I think I said that correctly this time.
I know it's Klenovich. Vladek Klenovich is a professor. Everybody knows Vladek. He's a professor of computer science at the University of Texas at El Paso. He went to school at St. Petersburg University. Well, it was known Leningrad State University at the time, I think. And he's has his degree or a PhD from the Sobolev Institute of Mathematics at Novosibirsk, which I guess was that in Novosibirsk? Actually, not a satellite campus, right? His research is all over computer science. It's hard to find anything in computer science that he has not touched. Vladek, I thought, had only 2,000 publications, but I learned that it's 2,400 publications. There is a time to slow down, Vladek, I think. I'm not sure when that is, but eventually there'll be a time to slow down. We're very pleased to have Professor Klenovich to talk to us today. Thanks.
Okay. Well, okay, let me share. Thank you very much for the introduction. And actually, to answer Scott's question, Novosibirsk in this sense was more like, in some sense, like California. So this was a campus 30 kilometers from the city, but kind of everybody says I'm living in LA. Same thing here. Everybody says this is Novosibirsk. Okay, so this is like a general description of the talk, epistemic versus aleatoric, granular computing, and ideas beyond that. And as Dr. Ferson asked me to do, this won't contain technical details. It's more about ideas and understanding. And I'll start with the very beginning with what people want. So in general, what do we want? We want two things. We want to understand the world. We want to learn more about it. This is kind of what science is about. And we want to change the world. We want to, for example, in terms of the tropical storm, we want to predict the past. That corresponds to understanding, to learning more. And we want to come up with measures that will decrease the negative effect, what areas to evacuate, and so on. So crudely speaking, it corresponds to science and engineering, but it's more general. And what I want to argue is in both cases, we get some systems of equations. So what does it mean to describe the state of the world? Well, usually it means we have to describe the numerical values of the quantities that describe our world. For example, if we have a mechanical system, we want to describe coordinates, velocities, maybe angles. And some of these values we can measure straightforward. Like, for example, if we can measure distance from my home to campus. Some we cannot measure directly. For example, we cannot measure directly, of course, the future value of the quantities unless somebody invents a time machine. So we need to predict these values based on some known dependence between the current and future values. Sometimes we have explicit formulas. That's what Newton's theory is about. We have explicit formulas for prediction. But in most cases, we don't have such explicit formulas. What we have is sometimes, at best, some system of equations that relates the current quantities and the future values of these quantities. And sometimes these equations include the values of some auxiliary quantities. For example, Newton's theory, if we want to predict the position of the star, there is an elliptic object, I mean the moon, elliptic object, everything is okay. But if you want to predict the position of the new comet, then you cannot use any explicit formula. We have equations that relate what? What we want is position of the comet to any moment of time and the parameters of this orbit and the parameters that we beforehand do not know. So what we do is we observe location of the orbit. Then we get a system of equations from which we find the parameters of this orbit. And then we predict the future location of the comet. So in general, we have some measured quantities, x, we have some desired quantity, and we have auxiliary quantities, like the properties of an quantities describing an orbit. We're not directly interested in them, but they are needed. So we have a system of equations that relate all these quantities. X is what we know. Y and Z are what we don't know, but we need to determine. And Y is what we are really interested in. So that was in terms of science. What if we want to change the world? Well, then the goal is what? The goal is how do we achieve some desired state of the world by making some changes. For example, if we have a spaceship and we want it to reach its destination, it goes to Mars, we need to sometimes correct the trajectory. In other words, we need to make sure that it goes directly to the destination. Or, for example, if we are designing an engine, then we have some efficiency criteria, we have some pollution criteria, that its pollution or the car engine does not exceed certain levels, and we need to find the parameters of an engine that satisfies these parameters. In this case, we have a similar situation. We have parameters that describe the current state of the world, x, which we can measure. We have the desired parameters of y, which are parameters describing the sort of intervention, like parameters of the engine or parameters of how we need to change the trajectory. And we need the parameters that describe the desired state. So in some cases, we have explicit formulas, but in more general case, what we have is, again, we know x and t, we know what we have, we know what we want, we have some auxiliary properties, and we need to find the parameters y. So we have a system of equations. Similarly, we have x and t. We know y. We want to find y and z, and y is the values that we know. Now, here, this was a very simplified kind of description, which doesn't take into account the uncertainty, or as I would say, granularity. So instead of exact value, we have a granule. And I'll give simple examples. For example, like measurements are never accurate absolutely, there is always some measurement uncertainty. And in metrology, it's typical for measuring instruments. Sometimes you have the probability distribution that describes the measurement error, but in many cases, all we have is the upper bound on the measurement error, which is guaranteed by the manufacturer of the measuring instruments. For example, if we, and this is rather typical for other devices. For example, if we set a thermostat for 25 degrees Celsius, it doesn't mean that it will preserve 25.000. There is some tolerance. So usually it may be like, I don't know, 24.5 to 25.5, or more realistically from 24 to 26. So in some cases, we know exactly which values are possible, which are not possible. In this case, we just get a set of possible values. So instead of exact values of the parameters, we have sets of possible values of state, set of possible desired state, and we need to solve the corresponding problem. Sometimes, in addition to that, we have what Professor Xie mentioned before, that some states we know that they're possible. For some states, we know that they're not possible. For some states, we have no idea whether they're possible or whether they're not possible. In this case, we have what can be described as a set interval. In other words, we have a lower bound, a set of states about which we absolutely know that they're possible. We have an upper bound, the set of states which we know that they may be possible. And that's kind of a more adequate description. Same thing about our desires. Sometimes it's kind of naive situation when we know absolutely what we want. It's true in some situations, but not in all situations. And usually what happens is, in some cases, we know the states which we know are desirable. Some states may be desirable, and some states are not desirable at all. So, and this comes with all kinds of complications. In addition to what is possible or what is desirable, we can also come up with some degree, for example, number from the interval 0, 1, indicating to what extent this particular state is possible or desirable. And I don't mean this necessarily as a subjective probability. It's more like students evaluate us when we teach on a scale of 0 to 5. Whatever, Likert scale, on a scale of 0 to 5, how good is a professor? And they put 4 or 4.5, whatever it is. And in a nutshell, this is what fuzzy sets are about. So, and this is one possibility. Another possibility, if we have some prior information, if we have some frequencies, as Dr. Minge mentioned before, then we can have a probability distribution that describes this. So we can call it a probabilistic granule. And it's possible to have a more general granule, including, of course, P boxes, C boxes, and so on, where instead of a single probability distribution in the P box, we have a family of probability distributions, in general, imprecise probability case. So, so what is the problem? So in many practical situations, we have a system of equations. So in this system of equations, we know X and we know T, some additional parameters that we know, and we need to find the values Y, while there are some other values on which contained in the equation which we don't know. In practice, instead of the exact values of X and T, what we have is the granules. It could be intervals, it could be P boxes, it could be probability distributions, and so on. So we need to solve the system of equations, but not in the normal mathematical case when the unknowns are numbers and the parameters are numbers, but in the case when all this is described by some uncertainty. So, and that's my main point, because naively we can think, well, this is a straightforward situation. We have algorithms for solving these equations, and all we need to do is extend this algorithm to the corresponding cases of interval, fuzzy, probabilistic, and so on. And there are known techniques for extending algorithms to the interval case, to the fuzzy case, to the probabilistic case, and so on. And here in practice, we get a problem. The problem is, in practice, these extensions sometimes work well, and sometimes they don't work at all. And that's kind of a shock, because practitioners, they like, okay, I'm exaggerating a little bit, but everybody likes recipes. Like when somebody comes to a statistician, they don't want the answer, okay, go look into my paper, go look in the book, go think. What they want is a recipe. They want to follow some algorithm. Ideally, the algorithm should be implemented already in the computer, and they want to produce an answer, and the answer has the imprimatur of the kind of confidence. Statisticians approve that. That's what people do in biomedical applications. That's what people do in engineering applications. And the problem is, and this is something that Dr. O'Hagan mentioned in yesterday's presentation, you have to think. Unfortunately, it's not enough to just consider the corresponding mathematical equations and somehow magically the solution will come. We need to know where exactly these equations come from. And part of this difference is whether they correspond to epistemic or aleatory uncertainty. So, and I will illustrate this on the very simplest example. It's not typical for this audience, but it's the straightforward, the most simple, and it comes from, again, measurement theory. If you have some measurements and you measure, for example, the temperature with your thermometer, and I'm just showing a thermometer, and the temperature is whatever it is in Celsius, 36.6, that in reality, the accuracy that they guarantee is probably plus minus 0.2. So it's somewhere between 36.4 and 36.8. They don't provide you any probabilities. And honestly, people don't care about the corresponding probabilities. So we're talking about very simple cases of uncertainty, which correspond to intervals. And the main intent of this talk, again, is pedagogical, just to help avoid typical mistakes. So we will give an example of two practical problems in which the equations are the same, the intervals, the granules are the same, but the practically relevant solutions are completely different. So the equations will be as simple as possible. So the uncertainty as simple as possible, it will be intervals, and the equations will be as simple as possible. The equation will be A equals to B plus C. I don't think there is any easier equation in the world. So first practical problem is the following. Suppose we have some amount of water in a reservoir, and then we release some amount B, and we would like to know how much water is left. So C is the resulting amount. So of course, A is equal to B plus C unless we have some loss of water. So if we know A and we know B, then the amount of water that is left can be obtained by simply applying this formula. C is equal to the difference between A and B. For example, if we had 100, whatever cubic meters, whatever it is, cubic kilometers, and B is 40, then the difference is 60. The second problem with the same equation is the following. We have some amount of water in the reservoir, and we're afraid that it will be, this amount is too large. If we keep it like that, the water may overflow and flood. So we want to release some amount. So as a result, we only have some amount B left. So again, what is this amount C? Well, we know that A is equal to B plus C. There's the same formula. So the amount that we need to release is the same A minus B. That's exactly the same formula as in the first practical case. And if we start with 100 units and we need only 40 units left, then we have to release 60 units of water. And we'll start with, again, very simple granules. So instead of considering the exact values of 100 and 40, let's consider the following. The value A is 100 plus minus 1, which is between 99 and 101. And the value B is 40 plus minus 2, which is between 38 and 42. And let's see what happens in both situations. So in the first problem, all we know about the original amount of water is what? It's somewhere between 99 and 101. And all we know about the released amount is that anywhere between 38 and 42. We don't know which exactly value it is. So again, we could potentially measure it more accurately. It's possible, but we're just dealing with the situation as it is now, when this is all information we have. So in this case, what we want to find how much water is left in the reservoir. In other words, we want to find the set of all possible values of this difference, A minus B, when A is in this interval between 99 and 101, and the amount that we released is between 38 and 42. So this is a simple case because this function is increasing in A and decreasing in B. And so in this case, it's easy to find the set. It's an interval. The largest possible value is when A was the largest and we release the amount which is the smallest. So we get from 101, we subtract 38, we get 63. The smallest possible amount is when we had the smallest possible amount and we released the largest possible amount, 99 minus 42, we get 57. And every number in between one can easily check due to continuity can be implemented. So that is the interval of possible values of C is simply between 57 and 63. Now let's consider the second problem. Suppose that all we know is that the original amount of water was between 99 and 101, and we want to make sure that after releasing the amount C, the remaining amount is between 38 and 42. In other words, we want to find all the values C for which no matter what was the original value between 99 and 101, the remaining amount will always be between 38 and 42. This must be some restrictions on what we need in the water so that it won't go too high and it won't go too low. So how can we describe the set of such values? Well, we want the value C for which this inequality, so that the resulting amount of water is between 38 and 42, will hold for all possible value A from 99 to 101. Again, this is a simple case. So in this case, we don't need any complicated mathematics or computations. We can just do it by hand. So first we reverse the signs. Instead of inequality by, we just apply minus to all the signs. We get C minus A is between minus 42 and minus 38. In other words, C must be, if we add A to both sides of this inequality, we get what? A minus 42 is smaller or equal than C. The C is smaller or equal than A minus 32. So this inequality means what? That C should be larger or equal to all the values of A minus 42 for all possible initial amounts of water in the reservoir between 99 and 101. So in other words, this is equivalent to requiring that C is larger than the largest possible of these difference. And of course, it's the largest possible when the original amount of water was the largest possible, 101. So in other words, the fact that this inequality has to be satisfied for all possible values A is equivalent to just one inequality. C is larger or equal than the largest of these values, which is 59. The right inequality means that C should be smaller than this for all possible values A. And again, it's equivalent to requiring that C is smaller or equal than the smallest possible value of this difference, which corresponds to the smallest possible value of A, which is 99. In other words, C should be smaller than 61. So we get an interval from 59 to 61. And this is different. In the first problem, we get from 57 to 63. In the second problem, we get 59 to 61. And this is, again, this is correct because like 63, it is a possible solution for the first problem. A possible solution when we had originally 101 units of water and we released 38 units. But it is not a possible solution to the second problem because if we had, for example, 99 units and we release 63, then as a result, we will get 36 units and we wanted the remaining amount to be somewhere between 38 and 42. And that's the reason for many problems, because what people do, they look at the equation, C equals to B minus A, unthinkably plug in whatever interval methods or probabilistic methods or fuzzy methods and so on, and get the result, which from the practical viewpoint makes no sense. So, and here is a more extreme version of this example. How do we get this extreme version? let's assume that vice versa, the accuracy of the original amount is plus minus 2. So instead of exact value of 100, we get somewhere between 98 and 102. And for the value B, we get 40 plus minus 1. So any value between 39 and 41. So for the first problem, it's almost the same. We get practically the same solution. Indeed, again, we want to find the set of possible values of the difference when A is between 98 and 102, B is between 39 and 41. Again, the function is increasing in A, decreasing in B. So the smallest value is when you subtract from 98 from the smallest value, the largest. The largest value of the difference when we subtract from 102, the largest value, the smallest amount. And so we get the interval between 57 and 63, actually the same interval as before. Now, what will happen to the second practical problem? When the original amount of water was between 98 and 102, we don't know more accurately. We want to make sure that once we release this amount C, the remaining amount is between 39 and 41. Well, here we get a problem because what do we want? No matter what the original value, we want to make sure that the amount we release will be between 39 and 41. We can apply the same simple arithmetic as before, reverse the signs, add A, and we get this condition. So this is equivalent to what? This left inequality, right inequality is equivalent to C smaller than A minus 39 for all possible value of A from 98 to 102. So it's equivalent to finding the smallest possible, smaller than smallest possible value, which is 98 minus 39, which is 59. So C should be smaller than 59. For the left inequality to always be satisfied, we want to make sure that this is greater than A minus 41 for all possible values of the original amount of water. And this is equivalent to substituting the largest possible value of A, which is 102. So we conclude that C greater or equal than 61. And of course, it cannot be, the number cannot be at the same time smaller or equal than 59 and greater or equal than 61. So the second practical problem has no solution at all. And this is, unfortunately, the typical situation. And in practice, it happened. And there were even kind of many papers who would say that like interval computations is wrong or probabilistic approach is wrong because they naively apply this idea of just simply plugging in this equation and using the usual interval or other techniques for taking into account uncertainty without thinking what actually needs to be taken into account. So the big question is, so if this doesn't work, if the naive approach wouldn't work, so what should we do? Well, this is a kind of very brief description of possible approaches. So suppose we have this situation. So we have this system of equations, f sub I, x, y, z equals to 0. There are q equations. X is known, y and z are unknown. And what we care about is only y. Z is unknown, but we're not interested in. This is like parameter of the comet or some other artificial auxiliary thing, which is needed to solve the equations, but we don't know. So what we want to find all the values y, possible values y. And what does it mean possible? That means for some possible value x and for some value z from this large value, these equations are satisfied. So this particular set unites, combines all the values y corresponding to all possible x and z. It is known as a united solution set. And this is in the case when we want to know the exact state of the world, which corresponds to epistemic uncertainty. Now, what if we are talking about the problems like control or decision-making when we need to change the world? Then we need to find all the values y for which, for all possible values x, the result should be in the desired range. That's typical the second problem of our water reservoir. In other words, for all possible values x, the there must be some value t from this tolerance set that satisfies all these parameters. So this, in other words, the set should be control parameters from this set. They should guarantee that it belongs to it. The resulting state will be desirable or tolerable. Desirable is kind of more strong statement. Tolerance is what engineers usually say. And so that's why this is known as a tolerance solution set. So how do we find the corresponding solution? Well, the general, but that's kind of the corresponding problems are NP hard. And that's kind of mathematical slang for saying there is no efficient algorithm that will always find exact solution of the problem. It sounds scary, but in reality, even solving systems of quadratic equations or many AI problems are NP hard. This is normal. In many cases, there are efficient algorithms for these problems. And the most well-studied problem is the problem of finding the so-called united solution set. In other words, we have an algorithm, we have some function, we know the parameters for the intervals of the inputs, and we need to find the interval for the output. In case of interval uncertainty, this is called interval computation. And the simplest way is called naive interval computation. And that's kind of why it's called naive, because many people naively think that that's what interval computations is about. It's not. It's more complicated, but this is what you start with. So basically, you take an algorithm and replace each elementary operation with a corresponding interval operation. What do we mean by interval operation? Like, how did we find the range of values of the difference A minus B when we knew the intervals for A and the intervals for B? Well, we used monotonicity. We knew that the function is increasing with respect to A and decreasing with respect to B. So the set of possible values of the difference, the smallest value is attained when A is the smallest and the amount that we subtract is the largest, and vice versa. So, and this can be described as the range of this difference applied to two intervals. This is called interval subtraction. Similarly, if we have addition, the smallest possible value is obtained when we add the smallest possible. Like, for example, if I have, well, okay, let's pretend that Scott is still in the US and has dollars in his pocket. I have between $10 and $20 in my pocket, and Dr. Ferson has between 20 and 30. So overall, the smallest possible amount is when I have 10, he has 20, so we have 30 total. And the largest is when I have 20, he has 30, and overall we have 50. For multiplication, it's not so straightforward because while it is kind of monotonic for positive A and for negative A, it's not clear, but for each A and B, A times B is a linear function. Linear with respect to A and respect to B. Linear functions, of course, attain their minimum and maximum at the endpoints. So all we need to do is to find 4 combinations of endpoints. The smallest and the largest will be the value of the product. By the way, in case you want to implement it, this is not the best algorithm. The best algorithm requires 4 multiplications. The best algorithm requires 3 multiplications, sometimes 2. But that's kind of the mathematical formula which is correct. For division, of course, if this interval contains 0, we don't have any bounded bounds. But here we can use the fact that in the computer, A divided by B is implemented. How? You take A and you multiply by the inverse. And that's inverse, of course, is a monotonic function. So we can have exact formulas for this one. So the resulting, and this is if we replace each operation with each arithmetic operation with intervals, you get what is called enclosure. You get the bound as a result for the given function, which contains the actual range of the function, which contains what we actually want to find. This enclosure is usually a drastic overestimation, very impractical. It's kind of similar to what in the probabilistic case we get when we get interval from 0 to 1. But there are efficient methods, which many, in spite of everything being NP-hard, which often work, and I just mentioned them. There is a central value method, monotonicity checking, bisection, and so on. So bisection is very straightforward. Methods work very well when the intervals are narrow. If the intervals are wide, we just divide them in 2 or in more and get good results. And this is a kind of, in politics, it's called divide and conquer. This is how, for example, during the Genghis Khan, the Mongols were able to conquer Russia. If you just take all the Russian people at that time and all the Mongols, the population was different, proportion was very similar. In principle, they would have defeated the Mongols by just, as they said, by throwing their heads at them. But of course, Russia was divided. And so one prince would call to the Mongols and say, well, let me, and they were all, by the way, relatives, let me kind of defeat my cousin and we'll divide his kingdom between us. And so the Mongols greatly agreed. And as a result, the whole Russia was conquered. Same thing how, I don't want to raise any nationalistic feelings, but that's exactly how British managed to conquer India. India, of course, always had a bigger population, but it was divided. So in politics, it's bad. In computing, it's vice versa. It's a very good idea. So how can this be extended to tolerance solutions? There is a technique called model interval mathematics. What does it mean, model mathematics? Well, the main difference is we look at the definition of the united solution and the definition of, so here we have only existential quantifier. All we care about is there exists some x, there exists some z. When we're talking about tolerance solution, some of the quantifiers are universal. We want to make sure that for all possible values of x, we get the desired state. So, and this is equivalent to the fact that, to the difference between possible and necessary. Possible means what? Something is happening in one of the possible worlds. Necessary means it's happening in all possible worlds. And this corresponds to universal quantifier. So the intervals corresponding to this inverse modality, to what has to be necessary, they are sometimes described as so-called improper intervals. For example, the upper bound is smaller than the lower bound. And they are also called Cowher intervals by the name of the researcher who introduced them. And they are indeed useful in solving the corresponding tolerance problem. For example, in that second problem, remember, we know the A and we want to find the value C such that for all possible values A, the result will be between lower bound and upper bound. So we have the tolerance interval, and we have the initial interval, and we want to find the value C for which the difference is always there. So we can have, like the arguments that we had before, lead us to the following interval, and you can trace that this is exactly what we had. We want to make sure that even if we have the largest possible amount, when we subtract the largest possible amount, we will still have, we'll still stay within the interval and vice versa. So, and this is exactly what will happen if we apply naive interval difference formula to the case when B is a normal interval with lower bound, smaller upper bound, but A is an improper interval where we swap the bounds. So this is the formula for subtraction. This is a general formula, but we swap the values of lower bound and upper bound, and we get exactly the tolerance interval. Of course, this doesn't work in more complex cases, but in more complex cases, we have to use more complicated situations. Okay, let me go back. Sorry. I think sorry.
Just to let you know, you have just over 6 minutes.
Yeah. Sorry. So I accidentally lost my point. Okay, yes. So similar thing can be used too in other situations. So let's show how this is applied to the practical problems. So in the first case, in the first example, the only information we have this interval A from 99 to 101. The only information about B is between 38, 42. This is the united solution set. So we apply a simple arithmetic operation with intervals, and we use the general formula. We get the interval from 57 to 63. In the second problem, we need to find the range such that for all A, the value B belongs to the interval. Here with A, we have a universal quantifier, so we swap the bounds because we are going from possible to necessary. And if we swap the bounds, we have the interval in which the lower bound is larger. We subtract from the lower bound the upper bound, from upper bound the lower bound. From 101 with bracket 42, we get 52. And that's exactly the range that we found by using the corresponding situations. In the second case, again, we have these two intervals from 100 plus minus 2 for the initial amount, 40 plus minus 1 for the amount that we of B, the water that should remain, or it does remain. In the first problem, we have just naive interval computation and get exactly what we want. In the second problem, what we get is we swap the interval and we get the interval from 61 to 59. So that's exactly what we concluded, that the actual value should be greater than 61 and smaller than 59, although here it represented in a kind of weird form of a non-improper interval, which means exactly that this problem doesn't have a solution. So, and this is exactly the conclusion that we made before. And of course, there are other formulations. We just considered the simplest case. But in some cases, for example, in control problems, we can divide control parameters into two groups. There are some parameters, for example, the design parameters that we need to select once and for all. And there are other parameters that we can change. For example, if we are building a heating and air conditioning system, some parameters are fixed and some parameters we can control by turning the knob. In this case, we have a more complicated problem. We need to find the parameters such that for all possible values, we can find the appropriate values of the parameter that will lead us to the tolerance set. This is known as a control set. Even more complicated situations appear in game time situations when we need to make decisions in the situation of controversy, when we need to make sure that for whatever solution we make, whatever the actual situation is, whatever action the adversary makes, as a result, we get to some good solutions. So conclusion. Well, in a nutshell, conclusion is very simple. When a practical problem reduces to a system of equations and we have some uncertainty, it's not enough to know the equations and to know the uncertainty. We have to take into account what is the problem. We have to take into account, and not just using the word aleatory or epistemic, we have to know exactly what we want, what is the situation, what are the equations, and if we do that, then everything should work. Of course, these are the simplest cases. I just wanted to illustrate the main difference of handling different types of uncertainty in situations which are mathematically absolutely the same. So thank you very much for inviting me, and I will be glad to answer any questions you may have.
Thank you very much, Vladek. The floor is open. If anyone wants to unmute their microphone, please go ahead and ask some questions or put them in the chat and I'll read them out.
Vladek, could you explain why you feel the need to use this word granule or granular? What are you hiding?
Well, I mean, that's the word that is used sometimes in our community. I mean, because the word uncertainty is too vague. And so granule is kind of terminology that some people use. I'm not insisting on it. Some people use to describe this kind of more kind of precise way of uncertainty, but I'm not insisting of this word.
Are the you talked about the forward calculations, the united case and the tolerance case. I guess, are there others that we should be aware of?
Yes, that's one case. Yeah, that's what I mentioned. That one case is the controlled solution, where we have some parameters which we select two types of parameters. So here we have, you have a different sequence of quantifiers because we need to fix design parameters such that for every possible values, we have the result should be tolerant. And in game type situations, it can be any number of quantifiers because we need to find a solution. For example, if we have several steps, we, I don't know, impose some sanctions on Iran. I mean, well, that's complicated. It's not numerical. But suppose this is like competition on the stock market. So you make some move, and in response, the competitors make some move, and so on. And so you need to go several steps ahead. And this, in each case, there is a lot of uncertainty. So you need to make sure that you make a move such that for every possible move of the opponent, there is a move of yours, such that for every other move of the opponent, etc., you get to some situation where you don't lose all your money. So yes, there are all possible situations which are described by as many quantifiers as you want. And unfortunately, they are practical, like working a little bit with situations in like financial economics, and there they consider this game theoretic type situations very frequently.
We have another question in the chat from Corrado Menka. Are Cauchy intervals applicable to all possible arithmetic operations?
Well, Cauchy intervals are not a panacea, unfortunately. This is like a heuristic idea. In some cases, they work. In simple linear cases, they work. In more complicated cases, they don't. So and there are many examples. So this is kind of another pitfall where some people, no matter what you do, no matter what kind of complex conclusions people make, and Cauchy is not guilty of that, there are people who just view it as naively as an algorithm for solving all type of problems. How they say it, if you have a hammer, everything sounds like a nail, and they use it. But even if you use Cauchy intervals, you still have to prove that this is indeed a correct solution, because it's not always leading to the correct solution.
Hi, Wadi. So thanks for your talk. In the beginning, you mentioned that generally we can extend multiple techniques for interval and fuzzy cases. And also, as far as I understand, we have to be careful when we use naive approach when calculating intervals. So, and I have a specific question. Let's assume we have 3 intervals or 2, and we want to draw a fit straight line. So is this problem easy to solve?
If we have, if we have several intervals and we need to draw a straight line, well, if we have several variables, then it's NP hard. It's not easy to solve. If it's one variable, then yes, there are explicit algorithms for that.
Yeah, and are there any known techniques to fit a line, straight line, or like do linear regression if you have a set of intervals?
Yeah. In case of one variable, yes, there are explicit algorithms for that, right? Well, it depends. So if you have interval uncertainty in both only in y, then it's just linear programming. You don't need to do anything complicated, because all you have is the parameters for y. If it is if you have uncertain parameters for x, it's a little bit more complicated, but it's also doable. So you can And if you're interested, send me an email. I'll send you some links to the papers where these algorithms exist, right? If you have several variables and you find linear regression, then in general, it's NP-hard. There are some algorithms, but as usual in interval computations, computing the exact range is NP-hard. Computing the solution of system of linear equations under interval uncertainty is NP-hard. So if only the y, so if you want to find the y as a linear combination of x sub I, if the only uncertainty is on y, then it's still linear regression, linear programming. Linear programming works perfectly, and it's a very efficient technique. If you also have uncertainty in the inputs, interval uncertainty in the inputs, then in general, it is known to be NP-hard, and there are some algorithms which sometimes work, sometimes don't.
Okay, thanks. And last question maybe relates to this. So in the output, when we solve this linear problem for intervals, what's the output we will get? So this will be a region or some confidence bounds for linear regression, or?
Right, it will be, so we are kind of not considering here confidence intervals because we're assuming that we know the interval which is guaranteed. It's like 100% confidence bound on the value. Right, and in this case, the output will be on the parameters. We have intervals, and if you want to predict the value y, that's also will be an interval of possible values, yes.
Okay, thank you.
Valerik, very interesting talk. Thank you. I have a question regarding the uncertainty, what you're describing here. Your uncertainty is from the interval, right? There's no randomness, if I understand correctly.
No, just to clarify, this was just to simplify derivations, nothing else. So I'm not assuming, I'm not saying that this is, because if you, in some cases, if we have same thing like A equals to B minus C, if we, in addition to knowing the intervals, we may know some probability distributions. I just illustrated the need to take into account different things. So yes, this is a simplified version. This is only describing a very simplest case when we don't know any probabilities, we only know the interval. In practice, we often have some information about probabilities. So we have, let me just look at this case when I mentioned, so this is, we're just considering the simplest possible type, but the main idea remains the same. If you apply the same problem with P boxes, you need to have the same differentiation between united set, tolerance set, control set, and so on, except that mathematics will become more complicated and it will not be such an easy arithmetic. But sorry, I just interrupted your question, yes.
Well, yeah, this is, you partially answered my question. The thing is that even in your simplest example, right, is there any value to adding the randomness to this interval? That's probably, it's one thing. And also this uncertainty with the randomness adding into it, is it still the uncertainty of the intervals, or is the uncertainty of this added structure of randomness?
Well, I mean, my thinking is the following. Well, in Russia, we say, "Всё из печи на стол мечи." Whatever you have in the stove, put it on the table. If we know probabilities, absolutely, definitely, we need to use them. So this is unfortunately the case when we don't have probabilities. But yes, absolutely, if we have some information about probabilities, we need to use it. And that will be the information about, so the interval, so all of that is information about the corresponding parameter A, B, or C. So if we have any quantity, we need to use all the information we want. In some cases, we know the bounds, that will be an interval. In some cases, we also have some information about probabilities of different values in the bounds. In this case, we have some probability distribution or some imprecise probability description, including the P box. So yes, absolutely. If there is always, the more information you add, the more accurate answer you get. I'm not, God forbid, advocating the not using some information.
I think dependencies will become important when you try to solve those problems with p-boxes, of course.
Absolutely, absolutely. And again, the same situation. If in some cases we may assume that they're independent, in other cases we have some bounds on the dependencies. So we may have some information about the joint distribution, we may have some information about correlation, and that's very interesting research area in which there are more open problems, of course, practically useful open problems than results, but definitely, absolutely.
Thank you.
Hi, Vladik. Thank you for your talk. I'd be interested in your general vision of interval computations, because for me, the more I learn about it, the more convinced I am that interval computations really are the future for computing reliable predictions or some things like that. So would you expect intervals to eventually be used like everywhere in UQ or catch on even to probability theory? Or do you think that there are areas where it's just well warranted to stick with sample-based implementations?
Maybe we should ask Tony O'Hagan about that.
No, I mean, interval, let me put it this way, that whatever information you have, if all you have is intervals, and that's unfortunately for information, fortunately for people who are doing interval computations, that's a typical case when we process some measurement results. And I can tell you this happens in two extreme cases when we only have intervals. Because where do you get probability distribution? Okay, let me maybe stop sharing. We get a probability distribution by calibrating the measuring instrument. So we compare the result of whatever thermometer I have with some standard thermometer that is so accurate that its result can be considered precise. As a result, this is not possible for state-of-the-art measurements. When you have, for example, like Hubble telescope or big accelerator at CERN, it would be nice to, and it measures something, it would be nice to have a more accurate measuring device nearby to compare, but unfortunately, this is not the case. This is the best we have, and often for these super devices, the only information we have is bounds, so we get intervals, and that's one of the applications of interval computations. Another is, for example, in geosciences, it's very expensive to prospect for oil and everything, so people use the measuring instruments which are as accurate as they can be. So there are no more accurate ones. Another extreme case when we only have interval uncertainty is industrial applications, where in principle we can calibrate every sensor, but as many of you know, sensors are nowadays cheap. You can buy them for a few bucks, but if you want to calibrate them, that's several $100s. So in manufacturing, people usually don't calibrate. They just use the bounds provided by the manufacturer, and that's it. And in this case, we need to use interval computations. But if you also have information about probabilities, definitely you shouldn't delete it. If you not using it, you will not get good results, because if you have information about probabilities, you can get much narrower estimates, much more accurate estimates for uncertainty than what you get if we use pure intervals. Let me give a simple example. Suppose you have n different uncertainties. So the value is like simple case. The value that you're interested in is the sum of n quantities. Each of them has some uncertainty. And this uncertainty is approximately Gaussian, for example. They're all independent. They're all from the interval from -1 to 1. If you only use intervals, you get from -n to n. If you take into account that there is a general distribution, which probably has 0 mean, for example, then you can use central limit theorem and conclude that the result is normally distributed with standard deviation proportional to square root of variance, square root of n, and for large n, you get whatever 3 sigma, 4 sigma, 6 sigma bounds, which are much, much better than the interval bounds. So no, definitely you shouldn't replace probabilistic estimates with intervals. Intervals are good when you only have interval information. My vision about the future is that hopefully interval techniques, because I think, like, for example, P boxes, why I like them very much is because they kind of, on the one hand, they provide interval uncertainty for the commutative distribution functions, but on the other hand, they are handleable. They lead to many feasible and very efficient algorithms. Many of them are implemented in the system that Dr. Ferson and others have implemented. So definitely part of the computation with P boxes includes some interval operations. And my vision is that intervals should be like part of this general thing, because in general, it's NP hard. We cannot have, well, we may have a unified theory, but we will not have a unified algorithm, because NP hard exactly means that we cannot have an algorithm that always solves all the problems. But that's kind of, interval is one of the bricks in the future building of a general theory of uncertainty.
So you wouldn't say that interval calculus really has a place in pure probability theory in that sense? That
no, I mean, interval, I mean,
because
from the viewpoint of imprecise probabilities, an interval is a very specific case. And that's a very typical. What is imprecise probability? Is when you don't know exactly the probability distribution, when instead you have a class of possible probability distributions. So intervals correspond to the case when you have an interval, for example, I don't know, 0 to 1 or 57 to 63. And the class of possible probability distribution are all distributions located on this interval. So definitely intervals are a particular case of imprecise probabilities. They are studied separately because there's a typical practical case because of measurement uncertainty, and two, because there are some efficient algorithms of processing interval uncertainty.
Okay. Thank you.
Any more questions? I think we have time for one more question before we move on to the open discussion. Okay, no? Well, let's thank our speaker again. Thank you very much, Vladik, for a really insightful talk and interesting questions and answers from everyone. I'm going to give a little reminder from Scott. So no biting, no eye gouging, no wrestling or hugging, and no hitting below the belt. Only vicious retorts are allowed. And our conversation for today is to discuss what would a unified uncertainty calculator even look like. If Vladik or Minga want to start off, maybe Minga, you've been quiet for a while, so maybe you want to start off the conversation.
Well, probably my uncertainty is a little bit limited in the sense I always thinking uncertainty, there is a randomness associated with it. So the unified uncertainty, as I was presenting, I was thinking that within the statistical framework, we have 3 paradigms. And within these 3 paradigms, exactly, actually, we were the targeting, everything has the same targeting, is the parameter of interest coming from the data. It's just the way we're describing uncertainty from different paradigms are different. But it appears that with this kind of artificial sampling and also with this random estimator kind of idea associated with kind of artificial samples, there will be kind of at least have a platform to get them together. For example, we actually experience combining inferences from Bayesian, Fiducial, and Frequentist together using the CD framework. So that's part of the reason we feel like there is indeed a unifier in the sense is that hopefully will be BFF, best friend forever. So that's what I'm thinking of that. So I feel like an uncertainty calculator, the random estimator, that kind of uncertainty, artificial data would be kind of play some role. That's my personal opinion. Yeah.
So this is my general question about those objects. I think that it's clear that they have good properties and everybody should be adopting them. They're clearly better than single confidence intervals and clearly better than the posteriors from Bayesians who can't say what their distributions even correspond to. But they'll only really be useful if we can compute with them, if we can use them in subsequent calculations, which of course the Bayesians say they can do. Can we do that with these sort of confidence structures, these CDs or anything else? And you know, Cox, I guess, said that you're not allowed to compute with them, but in practice, you can do some things. So maybe if we can find a way to reliably compute with them, we would save the world, right?
Right. This is, to me, I think probably open to everyone. This is, to me, this is confidence distribution, for example. It's like a consistent estimator. We do not have something directly associated with it. And then, but you have a variety of ways to computing, right? It's just using the likelihood I mentioned, normalize it, and using the fiducial solving the equations, or using the hypothesis testing, or even using the Bayesian. You can kind of using Bayesian, then afterwards you check whether the coverage is right, and then do the things like that. But I think the also much more calculators are needed. I feel like, especially for the more complicated problems. So this is kind of inversion idea from generating artificial data from the ABC. I feel like it's very attractive. It's just this very complicated data, even you don't have a likelihood function, you don't have explicit mathematical expressions. You can have just, as long as you can generating the artificial data, and then you manipulate artificial data, and then come up with conclusions. For example, you can manipulate get the artificial data matching with your observed data, and then those things you I get things right, and then you kind of rejecting something kind of exactly the ABC was trying to do. Under the CD framework, we can do that. But the question, of course, is that the ABC type of algorithm is computationally inefficient, and because you reject a lot of things. But I think along that line, more efficient algorithm, I feel like that will be very attractive, because this is going beyond the current models describing in statistics typically have explicit expressions of the models, instead of this kind of more complicated, like differential equations, solving equations, including the Valadics kind of equation, the algorithm, those kind of things. How would you be on top of that, adding the solution to get fake data structure and then getting that out? Yeah, I don't know. I don't have an answer. I think this is an open question, but I feel like this is a very interesting question. How do you calculate that, right? It's just in specific case, we know how to calculate that. But it's a more complicated, more general problem. Do we have the algorithm? We'll be able to do that.
Can I jump in here? So I think, kind of, again, talking about vision, I think it's a very good question. And we need to separate two different things, because I think from the practical, so from the scientific viewpoint, of course, the more general, the better. But I think the kind of the most interesting will be to consider it from the practical viewpoint, because from the practical viewpoint, the ultimate goal is to make decisions. And on the one hand, if you look at traditional decision theory, how absolutely rational persons should make decisions, then it kind of be proven, and it has been proven many times, that then the decisions should be described by utility function, and a person should select an alternative for which the expected value of the utility should be the largest. But unfortunately, and that's kind of leads us to the need to consider imprecise probabilities as the main, or probabilities in general, but I would say imprecise probabilities as the main way to handle uncertainty for practical applications. Of course, the problem is, as many of you know, that this is idealized description of how people make decisions. Like Hollywood, for example, tries its best to come up with predictions on when the movie will be liked by the people, and sometimes they do, sometimes they have a spectacular failure. So people do not always follow this. So I think we need to take into account also like fuzzy uncertainty, because fuzzy logic is kind of a weird technique, but it had some practical applications in situations when it's very difficult to describe in precise terms what exactly people want. Like two examples are the fuzzy rice cooker, which was popular in Japan at some point, or the smooth fuzzy controlled metro in Sendai in a Japanese city. The situation was, it's not like if we knew exactly what people want, if we knew what people mean by smoothness of the ride, then it would be very easy. Well, maybe not very, it would be easy to solve the corresponding optimization problem and find the optimal control. But unfortunately, this is very difficult to describe in precise terms. So this probably should be added to the unified uncertainty calculator when we are making decisions, that the goals and even the situation is sometimes described not in precise terms, but in terms of words of natural language, which are not so easy to translate into probabilistic or any other terms. But in general, the fact that algorithms are not always efficient, it's inevitable. It's not the question of algorithms, it's the fact that most problems in computing are NP hard, including many problems with P boxes, many problems with intervals, many problems with other type of distributions. And it's okay. Like, for example, everybody uses MATLAB, people use Mathematica, and sometimes you don't get a solution, so it's normal. Same thing with like neural networks, which Professor Minge mentioned. They don't always have solutions, but sometimes they lead to spectacular successes. So I think a unified uncertainty calculator should be kind of, well, I mean, if I can rephrase the Scott's gentleman type description into the term that we're all familiar with, let 100 flowers bloom. Of course, Chairman Mao probably didn't mean that literally, but that's the phrase that is expressing. I think that's unified calculator should include all 100 flowers, should include all possible algorithms in probabilistic case, an interval case, and fuzzy case, and whatever other approaches to uncertainty, Dempster-Schaffer maybe, other approaches for uncertainty for which there exist efficient algorithms and which has been used for applications. I don't think one specific algorithm can replace all of that. Just like in general, I mean, yes, mathematics tries to generalize everything, but algorithms for example, computing square root that were invented in maybe Babylonia or India, they are still used today in computers, and they are not replaced with any more general algorithms.
Also, I may add to that, Vladik, that the fact that in general there isn't, in general, if there is there isn't like an algorithm. Well, in general, if a class of problems is NP-hard, it doesn't mean that you can find a subclass of problem that can be solved in polynomial time. So that actually opens up to opportunities and to finding the subclass of problems that can be solved in polynomial time.
Well, yeah, that's the two main like challenges, as we say in interval computations community, is the following. Since the general problem is NP-hard, so we have two directions. One, find the classes of problems for which feasible time algorithms are possible. Two, find good algorithms that do not produce exact solution, but produce good approximations to solutions, because approximations make perfect sense. Sometimes the fact that we cannot find exact solution is no big deal if good approximations are good enough, because after all, especially in situations when we process measurement results or process expert estimates, the inputs are very imprecise. So why do we want to have unnecessary accuracy in the results? We can have what is called good enough accuracy corresponding to accuracy of the inputs, and that will be sufficient. And sometimes that helps a lot.
Can I suggest that the computability issues, although severe, I don't think that it's what is limiting us right now, because there are algorithms to combine distributions, with intervals and fuzzy structures, and people are working very hard to make those algorithms more and more available. But what is in short supply, or what seems to be the limiting step for us right now is, well, it's maybe two things. It's the thing you brought up, Vladek, which was the subtlety of when I apply a forward equation or forward calculation versus backward calculation, and that's not at all clear. How do you need the original algorithm designer to tell you what is the back calculation and what's the forward one, or can you deduce that from the existing algorithm? And the second limitation is about that computability for those data dependent input structures. So we know how to compute with C boxes or confidence distributions once we have them, but are they correct? I mean, do the answers also have the coverage properties, or do they also correspond to a stack of confidence intervals? That part's not perfectly clear yet, right? So we need to establish that computability and interpretability of the answers, and then figure out how to automatically apply the algorithms that we have to implement algorithms that are not simply all forward calculations.
Yeah, I can just say to that I agree. The only kind of comment I can make is that in simple problems, yes. But for example, I have colleagues like Rafi Muhana, for example, and he had a presentation by his student. It indeed works very well when you have few parameters. In big civil engineering structures, they have hundreds of parameters. At this point, computational complexity becomes a big issue. So he recently had a student defending his dissertation, David Betancourt, who actually used neural networks to help. So in this case, you train the neural network to, and the usual idea is this: you have a complicated algorithm which takes forever, like for solving partial differential equations. What do? You train a neural network to reproduce more or less accuracy the result of these hours of computations on high performance computers. And as a result, you have a simple approximate algorithm that produces that. So he did the same with uncertainty, and it seems to work very well. So I think neural networks from this viewpoint should be a big part of that, because they help to resolve these computational complexity issues in many cases.
All right, so that's just the newfangled version of surrogate models, I guess.
Yep.
Yeah.
I fully agree with this let hundreds of flower bloom, the idea. Actually, it's so complicated. We do need all kinds of idea, all kinds of algorithms, developments come in to really help us to address the practical problems. One thing as a trained mathematician, I'm always trying to think about, is there any kind of underlying thinking of ideas can be broadly reached to many of those applications? For example, I still going back as an example for me is I'm limited on this randomness kind of uncertainty issues. So in Vladek's talk, in the two examples, I always thinking, even I don't know the structure of the probability distribution of A and B, right? You only have interval. Can we assign like a random structure, say uniform for the A, for the interval? A low A bar is uniform and the B low is uniform. Then from that random generator, that kind of idea, get a solution. What the solution equivalent to what Vladek was presented? with that solution. So it's a little bit like a random algorithm, right? It's kind of thing you were thinking that generating A, generating B, solve it, generate A, generate B, solve it, and put them together. So collecting the set. It's a little bit, one is a kind of grid search. You can think of that way by defining what he was defining the interval, the C in the C set. But then you can also thinking of that, let's use a Monte Carlo method, randomly simulate A, simulate B, solving for it, simulate A, simulate B, solving for it. That is any equivalence, right? So things like that. Is any kind of, for the uncertainty, is there any kind of big idea to kind of unify in this way? So that not necessarily unify everything, but have a broad reach.
So I can answer that. This is actually, you mentioned a very good topic, because there are people who do that. And that's a big controversy in the metrological community, because International Standards Organization actually standardized this, and researchers are fighting against it, that every time you have an interval uncertainty, you assume that there's a uniform distribution. The reason, it's the arguments between companies that produce measuring instruments and researchers. Let me give you a simple example. Suppose you have n measuring instruments, and all you know, n measurements. From each of them, the result is somewhere between -1 and 1. So in principle, we don't know anything about relation between them, anything about correlation. The only thing we can conclude with guarantee is that the sum of these n values is between -n and n. On the other hand, if we do as you suggest and assume that the distribution is uniform, then we get uniform distribution on each of the intervals from -1 to 1. So for n large, the sum of these n random variables, according to the central limit theorem, is approximately Gaussian distributed, with variance proportional to n, and therefore standard deviation proportional to square root of n. So if you impose 3 sigma interval or even 6 sigma interval, you get bounds which grow not as n, but as square root of n. People in measuring instruments love that because it enables them to lower the accuracy of their instruments without making any changes in the hardware, while researchers are worried that in such situations, you may underestimate the uncertainty, and this may lead to catastrophic results. So a better way is, instead of having just a uniform distribution, to have several different distributions on the interval. And then you, instead of trying just only one distribution and running this simulation for that, you try all possible combinations of distributions, and that, yes, that will lead us to exactly the same result as. So from this viewpoint, from the mathematical viewpoint, I think imprecise probabilities are kind of a general unifying theme. The problem, of course, with general imprecise probabilities is that there is general mathematics, but there is no general algorithms. So to get to algorithms, you have to specify whether it's a P box or an interval or Dempster-Schleifer or something else. But yes, there are folks who have conferences and books on the regular basis. They have all these classes of distributions as a possible description. And maybe that's the way to go, because I'm also a mathematician by training, not a statistician or anything. And I definitely appreciate the need for the general formalism that would hopefully help us in designing this general calculator as well.
Yeah, that answers my question. That's yeah, it's still, but yeah, that's essentially, yes, that's true. It's not.
Just as a follow-up to that, I think you really need to look at the dependency of those measurements. So you really have a multivariate distribution, and that's a very different story. If they're all perfectly correlated, for instance, now you're still back to the -n to +n.
Yeah, even if they are not correlated, suppose each on the -1 to 1, suppose each distribution is bounded Gaussian, but with the mean not 0, but 0.2, you immediately get 0.2n as a result. So you don't even need correlation for that. But yes, dependency is also a big issue. Absolutely, yes.
Well, I was just pointing out that if you just try a bunch of different univariate distributions, but you assume everything is independent, you're really not capturing the range of possible.
Yeah, absolutely.
What it could look like.
That's for example, a common situation in a lab where you're taking the measurement from with the same instrument, and the same person is taking the measurement. So I think that's a very valid point, right?
Yeah, but yeah.
I mean, we have some strategy, you know, the Fréchet bounds. If you don't want to say anything about the dependence, there are ways to bound calculations that depend on those input variables. But as far as I know, there isn't a big push in statistics or any discipline to develop methods for better characterizing dependence functions. Maybe we should ask Minga can we generalize the notion of a confidence distribution to a multivariate confidence distribution that encapsulates, you know, not just the margins but the dependent structure as well? Or is that already done in some sense, or what do we have to do to sort of study these dependencies and be as and have as much confidence about the dependence as we do about the marginal distributions?
Right. This is actually a very, very tough question. For the dependence, actually, we try to incorporate some dependence with the kind of normal or Gaussian processes kind of procedures. But typically, the dependence is very, very difficult problem. In statistics, I think it's, you know, the Gaussian normal distribution, you have second moment can describing it, right? Correlation coefficient. But beyond that, the dependence is so complicated. You don't really have any clue what kind of dependence that would be or anything of it. In recent years, I believe there are there are several researchers. It's not top of my head. I'm not following that closely, but I knew that the several researchers, at least the NSF, has funded several grant proposals on this direction. It's just to use a non-parametric way to quantify the dependence. Before there was a push for copulars, but copulars is too much stronger assumption. So I personally don't think this is right. Mathematically beautiful, but not necessarily right thing. But what they were doing, this kind of non-parametric way to quantify the use the data to tell the dependence. You for example, just imagine you have X, Y scatter plots, and then just these scatter plots from the scattering points. Can you kind of tell me X and Y are dependent or not dependent? There are ways to test that. It's kind of very nice. This is kind of that kind of result. I think recently there are works on that. We definitely, if that can be modeled, we definitely can bring that into our confidence distribution or any kind of statistical framework. But the question now is that it's still a lot of research need to be done for that dependence. How do you describing it even? That's giving your data. How do you tell that's two sets is dependent? What kind of dependence you would be able to model? That's how it's really difficult. I think this is a lot of, and also I think most of the tests also a little bit data greedy. If you have like you just imagine you have 10 points scattered around, it's hard to tell it's dependent or not dependent, right? If you have thousands of points clouds, you can imagine the two-dimensional clouds. Not much easier task. So yeah, I think this is a really, really tough question, the dependence. We especially in high dimensional, we're at the pity of the whatever, the cursor dimensionality issues over there.
Right, where it matters, right.
Maybe this is an important question though. How do you get research funded that you want to investigate this dependency issue? Because it doesn't seem to me that it seems to me that there's a big gap between practitioners who are aware of the issue and the kind of mathematics that allows us to deal with the issue. And it's not necessarily clear to me how we can address that in a neat proposal to any funding body, either here or in the States.
Well, one way is to team up with practitioners. For example, I have some colleagues who get a lot of funding from NIH, if you team up with people from medical area, and then you can apply. Same thing like what Rafi Muhana, he is applying into civil engineering, so he gets grants from civil engineering. From purely mathematical viewpoint, it's difficult to get this funding, but if you team up with practitioners and apply to the corresponding granting agency, there are better chances.
So then maybe what are the big application areas where we think this is a big issue that's either appreciated by the people that are going to be reviewing the proposals, or that we've got good case studies where we can demonstrate that not appreciating this issue is a big problem?
Well, biomedical field is, of course, a big area of applications. Also, areas like hazard analysis, whether you're talking about natural hazards like earthquakes, floods, and everything. This is a big area which has a lot of funding because potential catastrophes are horrible. And so people are like predicting of hurricanes, weather predictions. These are all areas where there is a lot of uncertainty, and people do some research trying to predict what's happening. Climate change is also one such area, but this is so politicized. I don't know if it's possible. There is like too much fights and biting and everything that Scott Ferguson asks us not to do.
You might try something easy like gun control.
Yeah.
That is true. Like in engineering risk analysis, I've seen many analyses that say something has a 1 in 10 to the 6 or 1 in 10 to the 12 probability. And when I did careful analysis, I got more like 1 or 2% in some cases. So many, many orders of magnitude. Most of that was because of improper dependence assumptions, right, or independence assumptions. And sometimes that's also coupled with using something normal distribution, a Gaussian, which could be way off in the tails. So you combine that with the independence assumption, and it can be off by many, many orders of magnitude in risk analysis. And I've seen that on very expensive life or death systems where millions of people's lives are on the line. That's actually what happens in practice.
Yeah, that's I think Bill Overkamp yesterday had a list of those engineering failures, and of course the financial debacle in 2007 was, arguably a dependence failure, a failure to recognize the important dependence issues, and the way we get really catastrophic failures today in modern terms is when multiple things fail. Right, and that's under a condition of independence that's just not expressed.
Yeah, just one of the reasons why 2008 economic things failed was because the methods that financial folks used to estimate were based on the assumption of normality of distributions. So they calculated the standard deviation and they assumed that 3 sigma or 6 sigma deviations are not probable. And that's exactly what happened. And for that, they were not prepared. So, but yes, in addition, there is also dependency. Absolutely, yes.
So I have a question. I'm not sure yet if we can start right away with the unified uncertainty calculator. So I might try starting a little smaller with the unified imprecise probability calculator. And my question would be maybe also to the experts that have applied this. Would such a calculator only rely on intervals for expressing epistemic uncertainty and precise probability distributions for expressing aleatory uncertainty? Or do we actually need to be able to express mixed types of uncertainty because we just cannot say this is a clearly epistemic effect and this is a clearly aleatory effect? I don't know, or do we just need, I think Matthias Troffas already left, or do we just need to state our acceptable gambles and everything's good?
Well, it's definitely needed to check because there's a big difference between situations when there is actual value and we don't know it, like when you have some individual object, or it's like in measuring instruments or in whatever it is, you get a bunch of measuring instruments or thermometers, and all you have is their general characteristics. So in this case, no matter how accurately you measure one of them, it doesn't help with the others. You still need to take into account that there is aleatory uncertainty. There is a whole range of intervals for the whole bunch of them. That corresponds to, for example, like in manufacturing, typical situation is what is called tolerance. So when you produce something, whatever it is, like pieces of metal or parts of the airplane, whatever it is, they have tolerance. So the size should be, I don't know, like 10 centimeters plus minus 1 millimeter. So you don't know the probability, and you may find the probability empirically, but then they will change the manufacturing process, which they do all the time to make it better, to use other parts, and the probability distribution changes. So in this case, you have clearly aleatory uncertainty, which is slightly different. So yes, you need to take into account which part is aleatory and which is epistemic.
So to rephrase the question, would you say that probability distributions and intervals are the atoms, or would they be the atoms of such a calculator, or does there have to be something different? I don't know what it looked like. Maybe a fuzzy membership function.
Well, I mean, p-box, for example, but I mean, there are many atoms.
I'm not sure. So what I've seen from Scott and his group is that the p-boxes usually arise from a combination of intervals and probability distributions.
Well, you can view it. You can view it this way, but it doesn't help computationally. I mean, what is a p-box? Is when for each value x, instead of the cumulative distribution function f of x, you have interval of possible values. So mathematically, you are right. Computationally, it doesn't help. It's like same thing, like atoms is a good example. You may know all the properties of the atoms. It doesn't help you if you want to find out the cure against a disease, although in principle, everything consists of atoms.
I think because the other interpretation is also true, right? That for each probability level, you have a range of possible events. So yes. I guess it's an important question about, is it always appropriate to interpret the p-box in both of those ways and compute with it in either of those ways?
That's probably a good question to analyze. I'm sorry, I think I have to go soon. So thank you very much for all this, and I'll see many of you at the next time when this interesting conference continues.
Thank you so much, Vladek, and thank you on behalf of all the other participants and Scott and the Risk Institute for your participation. Thank you very much.
Thank you very much.
Sorry we strong-armed you into coming. Sorry.
No, I mean, I wish I could attend in person, but yeah. But the good news about this COVID is at every conference you have a lot of people. Normally you wouldn't see only half of them because they wouldn't be able to come in person, but coming remotely is easier. Okay, thank you very much. Bye.
Bye-bye.
See you next time. So officially the meeting is adjourned, but please feel free to continue the discussion if you'd like to stay.
Well, let's thank Minge as well.
Of course.
It's hard work talking, especially when you can't see anybody's face. I'll show you my face for a brief second. Or not. Okay, I won't do it at all, apparently.
Scott, actually, I need to go as well. So,
okay. Well,
sorry. Yeah,
that's fine. That's fine. Thanks very much. Thanks for coming and participating and setting us straight on these many issues. We'll be talking about you when you hang up.
Yeah, thank you. It's a really wonderful venue. Really nice. Happy to be here. Thank you for having me. Thank you, everyone. We'll keep in touch.
Thank you very much. Bye.
Bye.
So I asked Francis to continue recording thinking that we might go on like we did last night for an hour, but maybe people are tired at this point. But if anybody wants to continue talking, please let's do so. Otherwise, we can adjourn.
Radio silence.
Yeah.
All right. Well, thank you very much to everyone for attending, and we'll see you at the next session on the 15th of February.
Alrighty. Thanks.
Please have a nice evening.